For number 7, I already went ahead and filled out my totals. Again, in order to find any of the totals, I'm just going to add across to get the total, or add down to get each total. So for example, 40 plus 10 is 50, and then when I do 40 plus 20 plus 35 plus 25, I get 120. This total right here will be totaled across, and it'll double check as you total down. It's always a good idea to double check. So now that I have all my totals, it says if a person is chosen at random from all of those surveyed, this is a keyword right here, from all those surveyed. It says what is the probability that they would like a black car? So if it's out of everyone who was surveyed, that's going to be the total of 380. And out of those 380, what is the probability that they would like a black car? Well, out of everyone, the total number of people who liked black cars was 167. If we have 167 out of 380, that's going to bring us to 0.439 or 0.44 when rounded. For part B, it says, given that a randomly selected person is a faculty member, what is the probability that they would like a silver or red car? So if we're given that a randomly selected person is a faculty member, that means we're only looking at faculty members. Out of all of the faculty members, which is 120, so we know that it's going to be out of 120, what is the probability that they would like a silver or a red car? A silver or a red car, silver has 40 and red has 35. If I'm trying to see what it would be that either one of those would happen, I'm going to add those together, 40 and 35. So that's going to bring me to 75. So I'll have 75 out of 120, which will give me 0.625 or 0.63. Again, if they say silver or red, that means I'll count the silvers and I'll count the reds because I'm not picky between those two. Both of those will count for what I'm looking for. For part C, what is the probability that a person would like a red car or is a student? So, again, we're going to look at the people who like red cars. I'm going to draw a little dotted line to show us the red cars. And it says, or is a student. So we're okay with the people who want a red car, and we're okay with the students. So if I'm looking for either one of those, I'll add them together, and I'll get 121 plus 260, which is the totals from both, which will be 381. If I have 381 people for the red cars and the student, what I need to remember is that these 86 got counted for the student, and these 86 also got counted for the red car. So these people got counted twice. So I need to subtract that one time. When I subtract that, I get 295. And it didn't say out of a certain situation, so that's going to be out of everybody that was surveyed, which will bring us to a total probability of 0.776, which will be 0.78. For part D, they're asking if the events faculty member and black car are independent. If we're going to be testing for independence, we're going to say the probability of A intersect B equals the probability of A times the probability of B. If this holds true, then they are independent. So the probability of A could be faculty member and B could be black car. So the probability of someone being a faculty member is 120 out of 380. So 120 out of 380 times the probability of somebody liking a black car, which is 167 out of 380. And we're going to see if that's equal to the intersection, which is going to be a faculty member who has a black car, or favors black car, excuse me, which will be 20 out of 380. So if we do 20 over 380, that's going to be the same as 0.0526, and I'm just going to extend it a little bit so I can make sure that I'm comparing the numbers. And if I do 120 divided by 380, and then I multiply that by 167 divided by 380, I'll get 0.13, and I don't have to continue. I can already see that these numbers are not the same. So I can say these events are not independent because the probability of A intersect B does not equal the probability of A times the probability of B.